The goal of the course is basically to combine the material that would be covered in two different courses in mechanical or chemical engineering, fluid dynamics and heat and mass transfer, to try and package that for materials engineers within one semester, because the curriculum doesn't place enough emphasis on this material to spread it out over two. We try to teach all of the topics that are covered in both of the courses in mechanical or chemical engineering within the single semester, and that makes it, of course, a challenge to teach, a challenge to learn. The sticking coefficient, the fraction that actually gets absorbed may not be quite as high as in a two-semester sequence, but the goal is to teach all of that material. So the students are evaluated on two different criteria, which are the quizzes and exams of various types and the homework assignments. I weight the homework assignments very low in their overall grade, just enough to give them an incentive to do the homework assignments, but not so much that we have to worry about, are they collaborating or not. Basically, I don't care. If three of them turn in identical homeworks, just handwritten with different pens, that's great. It makes life easier for the grader. And so the homework assignments count for about 10 to 15% of the grade. In terms of exams, we have a math quiz at the beginning, the purpose of which largely is to help them to recall the math that they learned 2 or 3 years ago as a freshman or a sophomore and be able to use it for this course. Then we have 2 exams during the semester. Unlike other courses, I don't put them at the 1/3 and 2/3 points of the semester. I put them at the 40% and 80% points so that they can be fairly tested on the first third of the exam with a little bit of time to study, and then for the second third, and then the final exam at the end. The final exam has 2 parts. There's a closed book part and an open book part. Each student must individually finish the closed book part, and then they turn in that closed book part, and then they may open their books and do the open book parts. So the closed book part is largely qualitative. It's outline how you would solve this problem, or describe the difference between the turbulent and laminar boundary layers. The open book part is then very quantitative, very much centered around problem solving. And in every year that I've taught this course, it has also included an essay question, which varies from just as open-ended as describe a process with which you are familiar, and how the concepts learned in 3185 help you to understand that process more thoroughly. One other thing about the tests during the semester is that I give them in class during the lecture period, and then I grade them rapidly, and then the students during their recitation periods are given the opportunity to redo the parts that they got wrong. So this serves a number of purposes. One purpose is that it helps the students to really learn the material very thoroughly. That if they didn't get it right the first time, instead of just accepting a bad grade and saying, oh well, I didn't learn that, it forces them to really get a good handle on every single part of that exam. The average during the first part is typically around 70 or so. The average after they've done the second part is typically around 95 to 97. The 3185 in-class portion is composed of lectures and recitations. There are 3 lectures per week and 1 recitation. There's no lab directly associated with the course, but I try to make my topics and examples relevant to the materials project laboratory, which was 3082, which many students take at the same time or before or just after it. In addition, I've introduced a number of pedagogical changes over the years. One of those is this methodology of assessing how much the students understand, not only by a course evaluation at the end of the semester, and then modifying the course the following semester, but introducing also a course evaluation halfway through the semester, and then going beyond that by picking up a practice which I learned from Lori Breslow of the Teaching and Learning Labs, which has been adopted first by the Aeronautics and Astronautics Department, a practice known as muddy cards. Muddy cards are index cards which are handed out to students at the beginning of the lecture. Students then take those cards and over the course of the lecture will write down on them any questions that they have. Will write down what is the muddiest point of the lecture, what is the least clear, the most difficult to understand. I can then use that for immediate feedback, and right at the beginning of the next lecture can go over the muddy cards and say, okay, what did students not understand? I can answer their questions and go over something that might not have explained very well. I might even try an alternative way of explaining it based on the way the question was worded. One resource which is a part of OpenCourseWare that was put in is a lecture that I give every fall semester on September 11th, which is a September 11th Memorial Lecture. This lecture is something which I began writing out in detail somewhere around 3 months after the September 11th tragedy in 2001. And what this lecture covers is really how to place our work as engineers within the context of society. What are some positive contributions that we can make? What are some limits on those contributions? As careful as one might be as an engineer to try to focus on technologies which will positively influence people's lives, the lesson of September 11th is that even a civilian jetliner built to bring people together can be abused by people with sufficient hatred as a weapon of mass destruction. So therefore, as engineers, there is a need to try and steer our technologies toward positive uses, and also a need for faith that they will actually be used for the purposes for which we intend them.